Right, so let's have a look at some of these. So the first one is checking whether you know your prefixes. Okay, now it may be that you would have to look some of these up, and I would, in this instance, I would have expected you to do so, okay, because I couldn't remember what a little f was, and it took me about a nanosecond to actually Google it. All right, so in this case, what we've got is we've got the fact that a pico, okay, is times 10 to the minus 12, and f is a femto, which is a times 10 to the minus 15. A capital T is a tera, which is times 10 to the 12. And I'm sure you're all familiar with capital G, which is a giga, which is times 10 to the 9. Okay, and therefore, if you are putting them in order of increasing magnitude, you find that femto is the smallest. All right, then we've got pico, then we've got giga, and then we've got tera. And therefore, our answer there is D. Okay, so there is your first one. Then we come to question 2, checking that we can turn units into one another. All right, so we're not working as far back as base units here, because as you know, a joule is not a base unit, but we are simply being asked to express an ohm in other units. Now, to do this, think about the formula first of all. Ohm is the unit for resistance, which is current, PD divided by current. And the other things that you're going to need to be aware of here is that PD is the energy per unit charge. Okay, so if I just change colour, because now I'm going to switch over to looking at units. Therefore, the unit for the volt, all right, is going to be a joule per coulomb. All right, so if we go back, we're therefore saying that therefore the unit for resistance, and remember, you shouldn't combine the two together, okay, units and quantities, so I'll do it like this. The unit for the resistance, therefore, is the unit for volts, which is joules per coulomb, divided by the unit for current, which is the amp. All right, so let's think about that. But what is an amp? Well, in order to do that, we need to know what current actually is. And if you remember, current is the rate of flow of charge. So it's coulombs per second. All right, so what we've now got is we've actually got joules per coulomb divided by coulombs per second. Okay, now when we've got that, what we've got is we've got fractions and fractions. All right, so when that happens, this coulomb will drop down, this seconds will drop up. Okay, so what we end up with when we tidy all this up is we've got joule seconds and we've got coulomb squared on the bottom. So what we've got is joule seconds per coulomb squared. Okay, and that means that for this question here, the answer that we are after is B. It is this one here, okay? So a useful approach when you're faced with these kind of questions is start by writing out the formulae that link all of the quantities that you've got and that you're heading towards, and then start to do that in terms of units, all right? But don't equate units and quantities. Don't put them in the same equations. So don't combine V's and I's with joules and amps, all right? Or at least use it a different colour like I've done here to try and show you which is which. Then with question 3, we've got something similar. So we're now looking for Young's modulus, all right? Now remember, Young's modulus is stress over strain, okay? All right, and therefore we know that in this case, we know that strain doesn't have a unit, okay? So we know that therefore the unit for Young's modulus is going to be the same as the unit for stress, all right? And we know that stress is force per unit area, force divided by area. Okay, so once again, I'm going to switch my colours. So therefore, we know that force per unit area is therefore newtons per metre squared. So we know that that one is okay. All right, hopefully we can equate that a newton per metre squared is the same as a unit for pressure. And therefore, the unit for Young's modulus will be also the same as the unit for pressure, which is the Pascal. Okay, so there are your first two. They're absolutely fine. But now what we need to do is say, well, okay, let's tidy this up because C and D are taking us back to base units. So we need to eliminate this Newton, all right? How do we do that? Well, we use a formula that involves force. And the easiest one to do is force equals mass times acceleration. Because when we do that, we know that a Newton is therefore equal to a kilogram metre per second squared, okay? Because the kilogram is the unit for mass and metres per second squared is the unit for acceleration. So if we now plug that into our newtons per metre squared, what we've now got is we've got kilogram metres second squared, so that takes care of our newton, and then we've got another metres to the minus 2. So when we tidy that up, what we end up with is kilograms seconds minus 2, meters minus 1. Okay, now if we look at the two options we've got left, you can see that that is option D. So therefore that is a possible unit for Young's modulus. So our answer here must be that C is the one that we are missing. Okay. And yet more of these examples of units. Hopefully by the time you've gone through these again, you'll be feeling a little bit more confident with these. Right, once again, always think of the formulae. So think about charge. What is charge? Well, charge is current times time. Okay, so if we think about what that means for units, that means that a coulomb would be amp seconds. Okay, and therefore in this instance, we know that that cannot be the correct unit for charge there. Okay, if we then go to power, all right, what do we know about power? Well, power is rate of transfer of energy, it's energy over time, and therefore we know that a watt is the same as a joule per second. All right, now we also know that a joule is the same as a Newton meter because energy is the same as work done. So joules are equal to Newton meters. So we know that our watt is Newton meter per second minus 1. Now, if we go back to our previous question, all right, and that's where this is really important, you have your working there, we know that a Newton is a kilogram meter per second squared. So what we've now got in here is that a watt is a kilogram meter per second squared, and then we've still got our meter per second there. So if we tidy that up, we've got kilogram meter squared second to the minus 3. Okay, you can see immediately that this now matches that one there. Okay, the question is asking which one is it correctly matched to. Okay, and therefore at that point we can say that it is actually B that is correct. Okay, if you really want to, you can go back and you can do energy. All right, you can do energy because energy, remember, is our value, our unit for power divided multiplied by seconds. All right, so you can see whether that would be true or not. Well, if we take the value that we just had, kilogram meters squared seconds minus 3, if we multiply that by seconds, all right, because that would turn it into energy, then what we've got is we've got kilogram meters squared seconds minus 2, which is not what they've got here. So again, you could go further and you could check and verify that they weren't right. Then we come on to 5, which actually we have already started because we've already seen some examples of units that we can use for power in the previous question. Okay, so if you go back to your working again from question 4, right, I'll grab a random colour, we can see that up here we decided that yes, a watt was a joule per second. So we know that that one is okay. Right, you can also see that from doing that, we said that a joule per second was the equivalent of a Newton meter per second. All right, and therefore we can see that A is correct. All right, if we then keep going, we're now saying, well, okay, kilogram meters squared seconds to the minus 3. If we look down, that's exactly what we ended up with for our working for question 4. So that one is okay. So once again, by powers of elimination, the answer here is going to be D. And then the last one, looking at units, was looking for rate of change of momentum. Okay, so what we're saying here is we're saying rate of change delta P over delta T. All right, and what that actually is that is change in mass times velocity divided by change in time. Okay, so if we think about that in terms of our units, what we're therefore saying is we're saying that we've got kilograms as our mass, meter per second for our velocity, and then we are dividing that by time, so we've got another per second. Okay, so in that case, if we tidy that up, we've got kilogram meters per second squared. All right, and immediately you can see that that is in fact one of our options. That is option D, so that is our answer to question 6. Right, then we come on to questions 7 and 8, which were a little bit more lengthy in nature. So these were about specific experiments. The key thing to note here was that it didn't matter if you weren't familiar with the experiment, it's about skills. Now, question 7, you should have been familiar with the experiment because it was work on internal resistance that we've done in chapter 2. Question 8, it was a completely new one to you, but the skills should still be there to allow you to complete it effectively. But let's start with question 7. So how would you make a direct measurement of the EMF of the cell, stating the type of meter you would use? Now this, hopefully everybody realised that because we are looking at EMF, we are looking at using a voltmeter. Okay, a multimeter wouldn't cut it. You need to be specific and say that it's a voltmeter that you would measure. Okay, but the key thing here is how you would measure it. All right, it was not enough to just say voltmeter. You needed to say it was across the battery or the cell terminals. All right, that's the whole point. EMF is about what the cell has the capacity to supply when there is no external load. So it had to be across the battery terminals. Okay. Explain why this meter must have a very high resistance. Well, all voltmeters should have a high resistance, and the reason that they do that is because we don't want any current to travel through the branch, effectively through that voltmeter. Okay, so what we don't want is we don't want it to draw any current. Okay, because as soon as we draw current from our supply, then our EMF gets reduced, as hopefully you remember from chapter 2. So we didn't want to have a meter, we wanted a meter with very high resistance so that no current gets drawn. Then you were asked to show that the efficiency was V over E. Now, so many of you here scarily just put, well, efficiency is useful power over total power, and therefore that's V over E. V and E are not powers. They are measures of potential difference, all right? They are measures of electrical potential energy, which is not the same thing. So what you had to do here was you had to acknowledge that power is current multiplied by PD, all right? So these are all skills and very basic ideas that you should be familiar with, okay? If you do that and you say, well, all right then, what's the P in this case? Well, what's going into our circuit, it's the current and it's the EMF, okay? Because the PD that we've got being supplied to our circuit is the EMF, okay? And then if we compare that with the power that we've actually got coming out, it is a series circuit, so we've still got I, but rather than now having the EMF, we have what is called V, which is our load PD. That is the PD that was actually available to our circuit. Now, if efficiency is useful power divided by total power, then what it is it's simply saying, well, that's POUT over PIN, okay? And in that case, we have got IV divided by IE. Our I's cancel, and that leaves us with V over E. Okay, so very few of you were able to prove that that's where that formula came from, despite it being quite simple GCSE ideas. Then you had to add a voltmeter diagram and explain how you would use it. So 1 mark for getting it in the right place. Very few of you managed to do this. If you want to measure the EMF of a cell, you have to have your voltmeter across the terminals of the cell. The EMF is a property of the cell, not of the external circuit. All right, so that's where it needed to go. But how are you able to then use this to take measurements of both EMF and V? Remember, EMF is what comes out of the cell. So if we have our switch open, then what we have got is we've got no external circuit. So if we've got our switch open, it's going to measure the EMF. The second that we close our switch, okay, what it's going to do is we will have an external circuit, and therefore whatever is now coming out of the terminals will be that terminal PD. So with our switch open, we get the EMF, and with our switch closed, we get V, which is our load PD, or the PD that is actually available in our circuit, and now we've got that external circuit. Describe how you would obtain a set of readings. Several of you managed to pull something out here, okay? Key things here was, well, what would you need to do? In order to do this, you needed to use a variety of values for external resistance. So you needed to change the value of your external resistance for several different values, okay? So change your value for external resistance. A good tip here, whenever you're asked about taking measurements, say how many different ones you would use, okay? And as a little rule of thumb, at least 7 is kind of a magic number, All right, so at least 7 ideally, but you need to change for many values of external resistance. So if you didn't say more than sort of 3, then you shouldn't have got any credit for it. And then the second mark comes from stating precautions. Well, hopefully you remember that when you leave a cell on, it's going to start to drain the battery. So if we want a true representation of the EMF of our cell, in actual fact, we need to make sure that doesn't get drained. So your precaution would either be switch off in between, okay, or it would be repeating to check that your values hadn't changed, okay? Because actually, if you repeat it and then you hadn't, and then you'd notice that they'd changed significantly, you would no longer be able to use that data because the EMF would have been altered. And then lastly, state and explain how you would expect the efficiency to vary as the value of R is increased. Well, actually, you should find that the efficiency is going to go up. All right, think about what we said previously. We have said that efficiency is power in divided by power out divided by the total power. All right, now how do we work out power in this instance? We're looking at resistances, so we've got I squared R. Okay, now our R is our big resistor. Okay, so what we have is the total power that we've got being used up in our circuit is going to be the current in the circuit multiplied by the value of our resistor R. The total power in the whole circuit, including our cell, will be the same current because they're in series, but it's the total resistance in the circuit, which is our external resistor. But remember, somewhere in here we've also got our internal resistance. Okay, so what's happening now is as you increase R, well, those two are going to go. All right, so we're left with this thing here. Sorry, that should be lowercase r. As you increase the value of R, what you're finding is that R, as a proportion of R plus R, is going to increase, and therefore so will your efficiency. And then on to question 8. The key thing here was that it was all about skills and you had to read the information that you were given in the question. If you weren't prepared to do that, you were going to miss a great deal of details that you needed. So it was a simple experiment where you had 2 magnetic discs and they're placed on top of each other and they repel each other, and there is a certain distance between the 2 of them. So using calipers to take the measurements of diameter, the first thing you were asked to do was to suggest a way to reduce systematic and then random errors. Really important, if you still don't know what these are, read them from the summary sheet that I put together for you. Systematic errors are ones that occur time and time again. They affect each measurement by the same amount. Okay, so what you should do here is that you should make sure that you have zeroed your calipers. Okay, so make sure they have no zero error. All right, we don't want a zero error on our calipers. We don't want a false zero. Many of you made reference to calibrating it correctly. You were on the right lines, but you need to be more specific about what you actually mean, because I think what you meant is to zero them. Okay, if you couldn't zero them, what you had to do was you had to take a value for your zero error and subtract it from everything. Okay, so either of those would have worked. Okay, so there is an option to reduce the systematic error. Okay, then the random error, so these are things that are unexplained, things that kind of just make random results appear, incorrect, produce anomalies. Okay, now what they were doing is they were making a measurement of the diameter. Okay, it wasn't an experiment, so all they were doing was taking a single measurement of the diameter. The way to reduce effects of random error is to take several readings, okay, and take a mean. So reducing random errors is all about repeating the readings that you take and then taking a mean. Then some of you missed this one out, so please make sure you're reading carefully. Draw the sectional view of the magnet to indicate how D is measured. So you should have something that looked, excuse my shocking drawing, but you should have had something that looked a little bit like that. Okay, so that the edges here In fact, that's where it should be really. The edges here were measuring the internal diameter. All right, anything down here, you wouldn't have been able to take measurements of the internal diameter. Okay, so it's really important that you were able to use that to find the internal. Then you were asked to work out the volume of magnet B. Okay, this one was relatively straightforward, or hopefully it was relatively straightforward. I won't necessarily do all of it, but the fact is what you should do first of all is calculate the outer area of your magnet. So you do that using obviously pi r squared, and in this case that is that first reading. The outer area, or rather the outer diameter, is this 59.90. Okay, so you do that with pi 59.90 divided by 2, obviously because it's a radius, and also we need to make sure we are working in meters. So there was our outer area, all right, and that came out at about 2.81 times 10 to the minus 3. You do the same then for the inner area, okay, so the area of air, if you like, in the middle, and that was done using the value that we had here of 19.32. So you do the same process there, 19.32 times 10 to the minus 3 over 2 squared, and that then came out at 2.93 times 10 to the minus 4 meters squared. All right, you then look for the difference in area, so you subtract one from the other, and then you multiply it by the height, which is this one here, this 12.9, so 12.09 times 10 to the minus 3, and when you do that, you end up with a volume of about 3.05 times 10 to the minus 5 meters cubed. A few people went about this in slightly different ways, but as long as I could see what you had done, then that was absolutely fine. And then lastly, you were asked to describe how they could make an experiment to test her hypothesis that the force exerted on the magnet B by magnet A was inversely proportional to the height cubed. All right, so there are a couple of ways of achieving marks here, some to do with procedure, some to do with how you analyse it, and some to do with how you actually find value for K. All right, so those are the 3 bullet points that are down there. So the first thing, the procedure that could be used. All right, so what you had to do here was you had to get in there for somehow that for different masses of clay, okay, so different masses of clay, record the different values of H. Okay, and again, you need to say several, okay, don't just say one, you needed to mention that there would be several. All right, so for different masses of clay, record the value for H. Okay, because this thing was looking at F, not mass, you had to then work out force. So you had to get in there somewhere. Force is mass times gravitational field strength. Some of you were a little bit slapdash with your use of terminology. It's really important at A level that you know the difference between mass measured in kilograms and weight measured in newtons, because if you slip up you will get things wrong. Okay, so there were the main things in terms of the procedure. What you would then do in terms of analysing the graph, many of you got this right, so well done. That y equals mx stuff is starting to kick in. So what you were then going to do is you were going to plot f against 1 over h cubed. That's absolutely fine. You could have got credit saying that this should be a straight line. Okay, so that would have got you a mark if you said that it should be a straight line. All right, and then the last point here was to then say that actually if you did that, your gradient would be equal to K. All right, so your gradient would give you a value for K.